My name is Brian Bascoit, and I am a staff engineer here at DigitalOcean, and I work on load balancers. Today, we're going to dive into our load balancer architecture, how it has evolved since its inception, and how we have scaled to handle over 1 million connections for each load balancer, with capacity for serving hundreds of millions of connections across the fleet. For those not familiar with our load balancing product, it is a managed TCP, UDP, and HTTP load balancer. If you're using HTTP, there's support for automatic Let's Encrypt certificates, sticky sessions, so your clients are routed to the same backend, and more. We manage all of the software upgrades, redundancy, failover, and the automation to handle all of this for you. We also route traffic over your VPC to ensure secure connection between the load balancer and your application. The original load balancer architecture, released in 2017, was deployed using a droplet, which we call a load balancer droplet, and a reserved IP. This allows us to shift the reserved IP to another load balancer droplet if the primary becomes unhealthy. It also allows us to perform upgrades to the load balancer by spinning up a new LB droplet with the updated software, and then we can switch the traffic over. The downside with this approach is that during the period in which we switch droplets, all existing connections are dropped, and clients will need to reestablish a connection to the load balancer. After our initial release, we had great adoption, but we heard from our customers they needed to scale higher with more connections and more throughput. We launched T-shirt sizes with small, medium, and large sizes, and we scaled the load balancer droplet vertically. The original LB product was based on a 1 vCPU droplet, and the medium and the large were based on a 2 and a 4 CPU dedicated droplet. These larger sizes enabled a medium and large size load balancer to handle larger workloads. This allowed many customers to route more traffic through their load balancer and scale up their workloads. We knew that this wouldn't resolve all of our customers' needs, but it was an initial milestone on our journey to scale to higher and higher workloads. During the design of our next iteration, there were a number of goals that we wanted to meet. We wanted to scale to 1 million+ connections, high availability, while keeping the pricing simple. We wanted customers to have the ability to scale their load balancing layer, but also have a fixed price so that they would know what their bill would be at the end of the month. We accomplished this by adding an additional tier to our load balancer architecture. This new tier leveraged a pass-through network load balancer, or NLB, that we deployed onto bare metal. On the NLB, we leveraged BGP and ECMP to spread traffic across n number of servers deployed into each data center. We leveraged an open source project, Catran, which allows us to route connections to one or many load balancer droplets in an active-active architecture. BGP is a protocol that allows us to configure our network fabric on where traffic should be routed to within the data center. ECMP, or equal cost multipath, is a feature of BGP that allows us to spread traffic across many individual servers for a single IP address. This turns each load balancer IP into an Anycast IP within the DC network fabric. Depending on where connections are coming from, the network fabric will do a modulo hash on the 5 tuple of the connection to choose the closest server to route to. Each of our servers are deployed into a rack and connect to the switch in its rack and a switch in a sister rack. This ensures the redundancy if a switch were to fail or need to be taken down for maintenance. We can also tolerate one or more individual servers failing with traffic automatically routing to other healthy NLB servers. The downside of ECMP is when performing a modular hash, any changes to the topology of the network causes major disruptions to all existing connections or flows. Adding or removing a single server from rotation can cause a large percentage of connections to be broken, since they'll be rerouted to new servers that have no knowledge of those connections. Diving into each of these bare metal servers, this is where we run CatRun, an eBPF program. This is an XDP or Express Data Path program that sits between the path of the NIC, the network card, and the kernel networking stack. This allows for packet processing to be done directly off the NIC, which enables a highly performant load balancing data path where the NIC itself is the bottleneck on each of these servers. Our tests and real-world traffic show that we can saturate a 50 gigabit per second NIC with very little CPU usage. For those not familiar with eBPF, it's a feature of the Linux kernel that allows you to write custom C code that gets sandboxed and runs directly in the kernel space. There are various mount points that you can place eBPF programs, with one of them being XDP. XDP programs run between the NIC and the kernel networking stack before an SKB is even allocated to each individual packet. We're able to adjust packet headers, perform quality of service such as rate limiting, and it's also what powers our load balancing firewall feature. CatRun leverages the maglev algorithm, which is from a paper that Google released in 2016. Maglev is based on a connection table and a consistent hash of each packet. So as packets flow through the server, the connection table is used to determine which backend to route each packet to. If there isn't an entry in the table, we will perform a consistent hash on the packet to pick a new backend. An entry is then added into the table, so any future packets can be routed to the same backend. Changes to the network fabric can cause existing flows to be routed to entirely different NLB servers due to the modular hash that we discussed earlier. This can happen for any number of reasons, such as adding or removing NLB servers, either to add new capacity or to take a node out for maintenance. During these events, we will rely on the consistent hash of the packets to ensure stable routing, even though flows are being rerouted to new NLB servers. We take precaution to ensure that LB droplet maintenance and NLB server maintenance events don't happen or overlap, which has the highest potential to cause connection resets. This is because the consistent hash changes when we add or remove load balancer droplets, and making changes to the NLB fleet causes ECMP rebalances, which can cause connections to be rerouted to new NLB servers. These other servers don't have an entry in their connection table, so they need to perform a consistent hash on the packet. But a new backend is chosen since the underlying table has changed. This causes the connection to be reset since that LB droplet doesn't have that connection, which will cause a percentage of clients needing to reconnect. But this is quite rare. With the new NLB architecture in place, we now route all load balancer traffic through it. The NLB will load balance the TCP and UDP connections to one of the load balancer droplets. The LB droplet will terminate the connection and then will load balance traffic to the customer's application's droplets over its VPC. We also leverage DSR, or direct server return, so all the egress traffic that leaves the LB droplet goes directly back to the client. This reduces the load on the NLB layer, which only needs to scale to the size of the ingress traffic, which is typically quite less than egress traffic, effectively reducing our need by 50%. It also increases the performance since the packets need to take less hops on their way back to the client. This also enables us to scale load balancer droplets up and down, We can rotate LB droplets using maintenance events for software upgrades, and then we can shift traffic over to new LB droplets. We can now also gracefully drain connections from old LB droplets before shutting them down. Each load balancing layer has redundancy in place to enable high availability. We have many NLB servers in each DC to serve traffic. If one of them were to fail, a timeout on our BGP sessions would occur, and it would be removed from the rotation, and all of the traffic would be rerouted to other servers in the data center. The NLB layer also performs health checks on each of the load balancer droplets to ensure it is up and ready to serve traffic. If a load balancer droplet crashes or goes down, the NLB layer detects this and will stop routing traffic to it automatically. We then have each load balancer droplet that actively health checks the customer's application droplet. If an application droplet becomes unhealthy, we'll also stop routing traffic to it. With this design, each layer is deployed into an active-active architecture and can suffer loss at each layer. We have systems in place to ensure that if failure does occur, we automatically route traffic away from it. We can perform graceful scaling up and scaling down, so we don't abruptly close client connections during these events. We can perform maintenance on the load balancer during software upgrades and have minimal to no impact on your traffic. We do this by scaling up n number of new load balancer droplets. We shift traffic over to those new ones. We wait for the connections to drain on the old ones, and then we can shut them down. This is more graceful than our previous design. To summarize, we were able to horizontally scale out each customer load balancer. Customers can choose a size, determine how much compute they need to handle their workload. They can scale from 10,000 connections all the way up to 1 million total connections if they were to choose a size of 100. It also gives you the control to choose a level of redundancy that you are comfortable with for your application. As part of Deploy, we are releasing Global Load Balancer. This is under beta, which customers can opt in using the feature preview. GLB will support routing traffic to all DigitalOcean data centers, which enables you to build applications that are resilient to DC failures, or you want to place your application as close to your users as possible. Routing choices include active-active, which will route users to the nearest deployment of your application, or active-passive, which is also supported, which enables assigning priorities to each data center. If one DC fails, then we'll shift traffic to lower and lower priorities based off of your configuration. Additional built-in features include a CDN product that is served from over 300 plus POPs, network and HTTP level DDoS protections, and more. We hope you can try out our beta and provide your feedback. Thank you very much for attending my talk, and hope you enjoy the rest of Deploy.